Alright, here we are going to work problem 6.72 from your textbook. This problem is going to be adapted from what your textbook described. I'm just going to do it in a little bit different way. I didn't like the way that it was kind of written up. But I did want to demonstrate the idea of this Hess's law business, okay? Now what this is all about is we're going to use a particular property of enthalpy, which is the fact that enthalpy is a state function. Something called a state function, okay? And enthalpy is a state function. Now, why is that important and what does that mean, okay? It basically means that it doesn't matter how you go from point A to point B, that the enthalpy change for a particular process is fixed, okay? And that's going to have important consequences for us through this so-called Hess's law business, because basically what it means is there may be a reaction, but I do not know what the enthalpy change is that's associated with that reaction, and maybe I want to know. If I can sort of combine, or I like to say add, but combine is probably a better word, if I can combine information on different reactions that lead to the overall chemical process that I'm interested in, I can actually use the enthalpies for those reactions to figure out what the enthalpy change for this unknown reaction is. And this only works because enthalpy is a state function. I like to oftentimes describe state function as follows. Pretend there's two towns or cities, town A and town B. Town B is up at the top of a mountain, and town A might be down in a valley. The elevation difference, or I'll call it delta H here, okay? The elevation difference between town A and town B is always the same. Maybe you climb up the side of the mountain to go from town A to town B. You've undergone a particular change in elevation. Maybe you take a car and drive all the way around a long winding road somewhere else, end up at the same point in town B. It doesn't matter if you walk up the side of the mountain or take this long circuitous route in a car or bus. The elevation change between point A and point B is always the same. It is a state function, just like enthalpy changes are state functions as well. If you start at a particular set of reactants, you end up a particular set of products in a particular phase or state. You've got yourself a state function. It doesn't matter how you get from point A to point B. So we're going to use that to our advantage here. Now, how does these problems involving this so-called Hess's law concept work? Well, basically, what Hess's law says is that we can add together enthalpy changes for reactions that yield the desired reaction. Okay, let's see how that works functionally. So, reaction 1 and reaction 2, we may be able to look up enthalpy data for those reactions from the literature. Reaction 1 is taking nitrogen gas combining with oxygen to make 2 copies of NO gas. Okay? It's actually a pollutant gas that's present in the atmosphere. It reacts pretty quick, but nonetheless it's an important pollutant gas. We have a second reaction in which 2 copies of NO gas react with oxygen to make NO2, which is also an important pollutant gas. This one's brown in color, can lead to sort of a brown tannish coloration in polluted cities. Okay, so it's nitrogen dioxide. So nonetheless, we have these 2 reactions, and we know for the first one the enthalpy change is a positive 180.6 kilojoules. For the second one, the enthalpy change is a negative 114.2 kilojoules. And what we're going to do is use this information above this line to figure out what the enthalpy change is for this reaction. Now, I don't even know what the enthalpy change for that reaction is, but I want to calculate it based upon the information that I'm given. Can I do that using this Hess's law business and this idea that the enthalpy change is a state function? I think that we have a pretty good shot. Now, the way that this is usually done is you take known reactions, like the ones that we were given above this line, and you try to figure out a way that you can get to the desired reaction by combining these 2. Sometimes that requires reversing reactants and products. When you do that, you flip the sign on your delta H. Okay? If you reverse reactants and products, you have to flip the sign. Sometimes you might need to multiply all of the stoichiometric coefficients by an integer. Maybe you have to double them or triple them. If you do that, you got to multiply your delta H by that same integer. Okay, so those are kind of similar rules. Let's see how this one works. I think this one might be a simpler example just to see the idea and the spirit of how this works. And then maybe we can try a more complicated one in a subsequent video. So by combining reactions, what do we mean by that? Well, what I go looking for usually first is one of the products of the reactions and seeing if that's kind of like an intermediate. I can think of this as an intermediate. So for instance, it's NO. I make 2 copies of that here, 2 moles of that in this first reaction, and then I kind of like use it in the second reaction. I think of it that way, almost like sequential. Okay, I make it and then I use it. It just helps me think about this more. So it's produced and then it's consumed, and there's no net change with respect to NO. And that's actually a good thing, because notice that NO does not appear in our desired reaction. So NO actually has to cancel out. We've got to get rid of it. So notice I do these lines there. That's what I mean by canceling out. We have to have the same number of copies on each side of the arrow if this is going to work. Unfortunately, we have 2 on each side, so they cancel or it works out, okay? Now what about the other substances? Well, if I'm looking at what else I've got left, I don't see anything else cancel, so I bring everything else down. I bring 1 copy of nitrogen down. I bring 2 copies of oxygen down. And I bring 2 copies of NO2 down because they don't cancel. And sure enough, that is my desired reaction. So by combining these 2 reactions, I only had to cancel out one thing, the 2 copies of NO. And in fact, that was kind of a freebie. I didn't have to reverse anything. I didn't have to multiply by any integers. Sometimes you have to do that to get the desired reaction, okay? But in this case, I didn't. I just combined these reactions. I got the reaction that I wanted to know something about. I want to know the enthalpy about. Now, how do I find the enthalpy? Well, what you need to do is the enthalpy, or delta H, for the desired reaction is simply going to be the sum of the enthalpies for all the other reactions that were used to generate the desired reaction. Now here we only have 2. Okay? We have reaction 1, we have reaction 2. Reaction 1, as written, has an enthalpy associated of positive 180.6 kilojoules. On the other hand, reaction 2 has associated with it an enthalpy of negative 114.2 kilojoules. Now notice kilojoules units. You always want to check that. Sometimes when you're looking at problems in the book or on exams, I might give you kilojoules here and joules here to try to trick you up. Make sure they're the same unit, because you can't really add or subtract them effectively if they're different units of measure. Here they're both kilojoules, which makes things a little bit easier for me, right? So all I need to do to figure out or estimate the enthalpy change for that last reaction is do the math. Do the addition and subtraction. Figure out that 66.4 kilojoules is my estimated enthalpy change for my desired reaction. Okay? So this is a simple Hessels problem.